Okay, I think we'll get started. If you're coming to us from the G. N. Lewis project, I encourage you to go to the introduction to make sure this is the right series for what you're looking for. But otherwise, we'll get started talking about the central concept in Physics 1 here, and that is forces. And the formulation of physics that we're learning about, force plays the central role in determining the dynamics and motion of particles. With forces, which today we'll spend our time just kind of recognizing types of forces. We're not going to do a whole lot of calculations, and as we go through the next couple of days, we'll be calculating with forces. The formulation of physics, as I mentioned, that we're working on is dealing with forces. So this is arising from three so-called Newton's laws of physics, and they all are dealing with force. Today we're going to just deal with the first law, and then we'll go into the second law, third law, and then we'll come back to the second law. The second law is really going to be the main law we need for solving problems or for doing calculations. But this first law is introducing this force. So in the law, we see in the absence of a force, okay, or what we'll end up seeing here is a net force, an object. Now, an object needs to be defined here. Usually in a typical problem, the object will be obvious. So if we're talking about the motion of this pen, then this pen is the object. And I might be applying a force to this pen. However, what the object is isn't fundamental. It's just what we are thinking of. So let's imagine this pen in my hand here. The pen is also applying a force to my hand. So from another perspective, I'm the object. What is the pen doing to my hand? What's happening to the physics of my hand here because the pen is applying a force to my hand? So it will be, although it will be very natural to say, oh yeah, that must be the object, I want you to think about the fact that we need to identify the object, and depending on the type of question we're asking, the object might change, even in the same setup. Okay, so it says an object at rest, so meaning sitting still, and I'll come back and say more about that in just a minute. Sitting still will remain sitting still, or an object in uniform motion, constant velocity motion, will remain in that same uniform motion if we have no forces here, in the absence of force. Or to twist it a little bit, if we apply a net force, it would require applying a net force to cause an object that's sitting at rest to start to move, or one that is moving with uniform motion to change its velocity. So either curve, right, that change its direction, or to change its magnitude, either speed up or slow down. Okay, now this is actually redundant based on what we've talked about earlier with this idea of the reference frame. So if I'm sitting here holding this pen and it's at rest, right, that seems like this part, and it feels a little different than an object that's undergoing uniform motion. But imagine I'm holding this on this train car that we talked about last time, and we see, and you're standing on the ground. If I'm holding it in this train car and we're moving at uniform motion, say 5 meters per second, then my pen is in uniform motion, right? So there really isn't an object at rest depends on what the frame of the observer is in. And so really this is all the same thing. We can always be riding along with the object to find the object's so-called rest frame. We're in the frame where it's sitting at rest. Or we could always be observing the object in a frame that's moving relative to that object. So a little more words are needed than what are said here than what are actually needed. So really you can get the first law boiled down to, in the absence of force, an object in uniform motion will remain in uniform motion. Or, in the absence of forces, an object at rest in its rest frame will remain at rest. Okay, well, in a sense, we have to kind of see what we're talking about when we talk about forces, and then connect that back to our own personal experiences. It's a little bit harder to talk about a force as it is, say, a position. We see this is sitting right here in this coordinate system. We're thinking about a force as something that is acting on this object. And so let's just look at the characterization of forces, the types of forces, and then a catalog of forces that just in our day-to-day lives we have experience with, and ones we'll run into. Okay, so, and this will bring in a couple of new definitions. We already have force, new words. We have force, we have object. Okay, now we're going to, these forces will act to either push or pull an object. And schematically here, I have us pushing a box. So in this case, we think of the box as the object. Here we think of the box as the object, and here now I'm pulling the box. The forces act, so the forces push or pull, and they act on the object. So we're talking about the forces that are applied to this particular object. Okay? So we have a push force or a pull force. It's acting on the object. Now, of those forces, we have two main types. We have a contact force, in which the agent, so a new word here for us now, the agent is what is doing the force, right? It is what is acting on the object. So in this picture, our brains would immediately say, oh, the box is the object, and we are the agent, right? But from another perspective, the box is pushing back on us. It's resisting our motion. We're trying to push it across the floor, and it's trying to keep us from doing that. So it could be the case that we're the object, and this is the agent. So I guess I want to impart this idea that we apply the word object or the word agent based on the specifics of the problem that we're looking at. So if we're talking about what is the box doing, then it's the object, we're the agent. Now, in both cases here, we are in contact with the box. Here, directly, our hands are actually touching the box. And here we are too, in that we have a rope attached to the box. Okay. Now, we also have what are called long-range forces, and we won't get to those immediately, but certainly next semester we'll be spending a lot of time with that. And that is your experience with charged objects. So if you rub a balloon on your head and then you try to put it near the wall, it want to be attracted to the wall. So there'll be a force, an electrostatic force from a difference in charge, plus charges and minus charges, will want to attract. There'll be an attractive force, even though they're not in contact yet. So they can act at a distance there. So that's a long-range force. They're not in contact. Now, forces are a vector quantity. So we've talked about scalars and vectors. And so it has a magnitude and a direction. And so thus, like any other vector, it will add vectorially. So in our pictures here, it would add, if this is F1 vector and F2 vector, then the F total, or F net, would be in that direction. So we could, and this is why we have the word net here. Let me just take a little aside here. We certainly could have a situation where we have some forces, where we have, say, a downward force F1 on an object and an upward force F2. They're equal but opposite directions. So as vectors, we would add head to tail, down, up, and we would have a net force of 0. This would satisfy the conditions of the first law. Even though there are forces present, the net force is 0. And when we talk about a net force being 0, we mean in the vector sense. The addition of all the different arrows bring us back to the tail of the first arrow. Now, when we have an object, and I think I'll give myself space to make another drawing after this. We have an object and we apply force to it. We can break that force, we can decompose that force into a tangent force and a tangent component of the force and a normal component of the force. Tangent means forming a tangent with the curve, with the surface, whether that's curved or flat. At any point in the surface, we have a tangent line, and the force is acting along that tangent line. So let's say we have a round object. If we're acting here like this, that's a tangent force. Here would be a tangent force. This would be a tangent force, and so on. We also have a normal force. Normal means perpendicular to the surface. Now, if we have a box, then it's pretty easy to see the perpendicular. There's perpendicular force, there's a normal force, and so on. The tangent force would be like this. That's a tangent force. But what we mean by normal is locally, or right at that one point, it's orthogonal to the surface. So let's draw our circle again. A normal vector, the normal force would be pointing in this direction here, this direction here, this direction here, or inward, right? That's also normal, just directed inward. But it's perpendicular, it's locally perpendicular here. So if we draw a tangent force and a normal force, we have perpendicular vectors at every point on the surface of an object where force is being applied. All right, and then we'll just finish today cataloging different types of forces. So these are all ones you've experienced and are familiar with. The first of which is called a weight force, and this is due to us having mass, or objects having mass, and near another massive object, and usually a much larger massive object. So here we're talking about, say, this pen, which has mass, in the gravitational pull of the Earth. And so when we're talking about scales, distance scales, that are much, much smaller than the radius of the Earth, then for all intents and purposes, the gravitational pull of the Earth is constant. Now on bigger scales, it certainly isn't. So a very distant planet in the universe doesn't feel any gravitational pull from Earth, whereas our moon does, and then of course we feel it very strongly here on Earth. We're going to, all of the physics we're doing in the next few days is going to be in the situation where we're close to the surface of the Earth. We will spend one chapter where we're talking about gravitational force, where we're at distances further than the radius of the Earth. But if we're close to the surface of the Earth, then the Earth's gravitational pull will cause an acceleration of a mass by an acceleration equal to g. G is a vector, an acceleration vector. It's pointed straight down. It's always pointed straight down towards the center of the Earth. And the magnitude is 9.8 meters per second squared. So we've seen this number before. That is the magnitude, and it's then always directed downward. And then m, of course, is the mass. So if you multiply the mass times the acceleration due to gravity, you get weight, and weight is a force. A force has units of newtons. So the SI unit is a newton, and newton. Notice it's a compound unit. This is mass is kilogram, and then this is meter per second squared because it's an acceleration. So a newton is a kilogram meter per second squared. All right. Another important force is what's called a restoring force, a force that wants to, or I guess I should say, is a spring force. It is a class of restoring forces. And what a restoring force is if we have a system that is sitting here, and then we displace it from that spot, there's a force that wants to pull it back to that spot, regardless of how we displace it. So if this is attached to a spring, and I pull it this way, the spring will want to pull it back this way. But if I push it this way, the spring will want to push it back this way. And so here we see a mass on a spring that's attached to a wall, it's compressed, so then it wants to push this way. Now we've elongated the spring, and it wants to pull it back to some so-called equilibrium position where the force is 0. So the spring force will pull back the object, and it will pull back proportional to how far the object has been displaced. So if it's just barely, you've barely displaced the spring, then the restoring force is small. You have a big displacement, the restoring force is big. So you've had experiences stretching springs. If you stretch, you can stretch a little, but then as you try to really stretch the spring, it gets harder and harder and harder. Okay, well, their restoring forces are more general. Really, any force that's trying to push something back or pull something back to an equilibrium position, in that general category, we'll talk about a spring-like force. So a pendulum is a good example. Now, when we talk about a pendulum, we have a mass on a string here, and if it wants to sit straight down. If I pull it up a little, it will want to come back this way. If I pull it up this way, it'll want to come back this way. So it behaves kind of like a spring, so we call it spring-like. The origin of this force is the weight of the mass, so it really is a weight force. But and this next force we'll talk about, tension. It's a weight force and a tension force, but its behavior is spring-like, so we can think of that as a spring-like restoring force. Tension, another important force. This is force exerted through a rope. So if we tie a rope to this box right here, and we pull on that, there's a tension force applied to that box that's mediated by that rope, and it's always in the direction of the rope. So if I'm pulling here, the tension is along this rope. If the box was really big and I was really short down here, and I was pulling down like this, then the tension is is angled down that rope. So always along the rope. So tension, force along a rope. Friction. Friction is a tangent contact force, which means it is always tangent to the object, because that's what it means to be tangent. The object is in contact with a surface, right? It's contact with the surface, and that force always opposes motion. So the direction it takes on is such that it is opposing the motion. And so I think the classic example here would be, let's think about sliding this box on a floor. So if we have a smooth gym floor, it might be easy to push that box. But if we take it out to a parking lot on concrete, it might be much harder to push that box, because the frictional force is due to the contact between the surface and the box. So the frictional force depends on both the surface and the object itself. And when we try to push the box across the floor, if I'm pushing it in this direction, the friction is trying to force the box back this way. If I'm pushing the box in this direction, same box, same surface, if I'm trying to push the box this way, then the frictional force is pointing in the opposite direction. Now, the frictional force actually breaks down into two types, static and kinetic or dynamic. So let's imagine this box sitting still on a platform, like a 2x4 or something, and we start to lift it up like this. When we first lift up a little bit of an angle, right? If this was ice or something, if it was iced over 2x4, as soon as we lift up as an angle, that box is going to start to slide down because there's no friction there. The ice is there. It's almost frictionless. But if it's not iced up, there's some friction between the wood surface and the box itself. So we can lift it up like this, and the box will just sit there. The box is sitting there because although gravity will want to pull it down this way, the frictional force will oppose that motion such that it just sits still. And the frictional force will just be whatever it needs to be to counteract the gravitational force so that there's no net force and that we're sitting there at rest and remaining at rest. That type of friction is called static friction. Now, if we keep pushing, if we keep pulling this up, eventually the friction is not strong enough, the static friction is not strong enough, so the box will begin to slide. And although the box will begin to slide, it won't slide as fast as if this was iced up. So there'll be a resisting force to that motion, and that frictional force is called dynamic friction or kinetic friction. Kinetic friction. So either kinetic friction or dynamic friction. Now, static friction is always slightly bigger, slightly stronger than dynamic friction for the same box. So, and you probably experienced this. If we lift this platform up, once the box starts to move, once the box is moving, if we were to drop this just a little bit, the box would continue to keep moving because the dynamic friction in this setting is not quite as strong as the static friction. That has to do with how the surface, down at the molecular level, how the surface is traversing over itself. When there's motion, there's a little bit less settling into the surface, and so it can't hold on to that surface quite as well. All right. Now, we have a very closely related force, even though it will seem a lot different, and that is this idea of drag. So drag, in a sense, is a frictional force, except we're not moving across a surface. What we're doing is we're moving through a fluid. And a fluid is either a gas or a liquid. So if we are moving through a liquid or a gas with an object, that has to push its way through that fluid. And so there's a resistance to that motion. So again, it's always going to be a force in the opposite direction of the motion. So the drag force is in the opposite direction of the motion. And depending on how thick that fluid is, right? If we try to swing a stick through the air versus swinging a stick through standing in a swimming pool, it's going to be much harder to swing that stick through the swimming pool because there's a bigger drag force due to the many, many more water molecules per unit area in a swimming pool than there is air molecules in as we swing through the air. And so drag is like friction is opposing motion. So you've experienced drag when you're trying to ride your bicycle. As you go faster and faster on your bicycle, you're trying to move through the fluid faster. You're getting more and more drag, and it becomes harder and harder to move through that fluid. So the drag force is proportional to the velocity. And just exactly how it's proportional to, we'll get to that in just a bit. Whereas the dynamic friction, it is the same regardless of the velocity at which the box is sliding. Okay, so a slight difference between friction and drag there. All right, so we aren't really doing a ton of calculations yet. We will very soon now. So your job in the next few days then is to really internalize some of these ideas of forces, be able to identify an object and an agent, determine if the force is a pushing force or a pulling force, is it a contact force or a long-range force, think about force as a vector, and then be able to if I were to give you a picture of something and say identify all the possible forces, be able to label them appropriately. All right.